Okay, so welcome everyone. Get the door. Thanks for joining us. My name is Simon Johnson. This event is part of a continuing series of micro-conferences hosted by the Stone Center on Inequality and Shaping the Future of Work, which I co-direct with Doron Astomoglu, sitting here, and David Walter on my right. Our mission is to analyze the forces that contribute to growing income and wealth inequality through the erosion of job quality and labor market opportunities for workers without a college degree. We identify innovative ways to move the economy onto a more equitable trajectory by carrying out cutting-edge research, developing curricula, and convening students, scholars, policymakers, and practitioners. The purpose of this event series is to highlight the latest research from our affiliates and colleagues related to our mission and to build a community of practice of scholars at all career stages. The format for this micro-conference, same as other micro-conferences we've held. Each speaker has exactly 25 minutes to present without interruptions. Then we have 10 minutes of Q&A, so please hold your questions until that Q&A time. And we will take a 5-minute break at 4:40 after the first presentation, but no break between the second and third presentations. We will run until exactly 5 to 6. Our first speaker is Ashesh Rambachan. He's assistant professor of economics at MIT, research interests primarily in econometrics with a focus on applications of machine learning in economics and causal inference. 25 minutes, over to you.
Great, thank you. Thanks so much for the chance to be here. So today I'm going to be talking about this paper, What is a Foundation Model Found? This is joint work with Keyon Vafa, who's a postdoc at Harvard in computer science, Peter Chang, who's a student at CS here at MIT, and Sendhil. So really the plan that I'm going to do today is I want to talk just a little bit more generally about foundation models, how they're beginning to be used in economics, and in particular what we're trying to think about in this paper is how we can learn about the structure or what we call world models that they encode. So as a starting point and a bit of background, traditionally in supervised learning, we focused on building specific models for new problems. So each model would be trained individually using large supervised data sets collected for the specific task on hand. So as an example, think about a spam filter or an image classifier trained on ImageNet. Foundation models fundamentally change this picture. So foundation models instead are pre-trained on massive diverse data sets, often using unsupervised or self-supervised techniques. And these foundation models are then adapted or fine-tuned for many downstream tasks using much smaller supervised data sets. So in this sense, they serve as a common quote-unquote foundation upon which many tasks can then be solved. So underlying this move to foundation models is the broader view that by pre-training these models on such diverse data, foundation models uncover some deeper structure, what we might call a world model in machine learning or AI, that makes them more broadly useful across a wide variety of tasks. So, of course, this is a conference for economists, so the natural question is, in light of this, why should we as economists care about this? Well, one obvious answer is large language models. GPT-5 and other large language models are pre-trained foundation models in language that we use across a variety of tasks, both in the economy and in our own research. And so understanding their properties may help us understand where they may or may not be useful. However, taking a step back, I want to argue that economists should care about these questions at an even more fundamental level. And in particular, that is behind almost all structured data that we analyze in economics lies a mess of rich, unstructured data summarizing economic behavior and outcomes that we care about. So, as an example, in labor economics, we analyze workers using coarse representations of their labor market history, think experience squared, the NAICS code of the industry in which they work, and we then use this coarse representation to study a variety of downstream economic questions, such as wage disparities, questions surrounding human capital accumulation, how employers learn about employee skill. But of course, these representations we use in practice leave behind a rich, unstructured data about the entire sequence of a worker's job history, about their past jobs, their past unemployment spells. Think about all of the information that might be captured in a resume, for example, that we don't bring to bear. Of course, the same idea applies in many other fields. For example, in health economics, we may analyze patients using coarse representations about what happened during a particular hospitalization. Think of a final ICD code summarizing the final diagnosis as a result of the visit. But this, of course, leaves behind the entire sequence of clinical actions that happened during the hospital visit. In finance, we analogously summarize portfolio holdings using course characteristics like market beta, market to book, momentum, rather than analyzing the entire portfolio holdings of a mutual fund, hedge fund, or investors. So as a result, we may be thinking about how could we use foundation model architectures in economics, such as generative sequence models, in order to better use this rich, unstructured data that underlies our analysis. And of course, across all of these three examples that I've mentioned, we're already seeing economists importing these ideas of foundation models into empirical work, in labor economics, in health economics, and in finance. All of these papers have come out in the last 18 months or so. So again, taking a step back, foundation models are AI tools that we pre-train on massive diverse data sets, often using unsupervised or self-supervised techniques. These foundation models are then adapted or fine-tuned for downstream tasks using small supervised data sets on the task at hand. And so for this talk, I want to focus a little more specifically on foundation models that are going to be pre-trained to predict sequences. So think of pre-training to do next token prediction. And of course, large language models and all of these examples of foundation models in economics are trained using those objectives. So in the context of this paper, what we want to spend some time thinking about is the underlying promise behind foundation models, which is that by learning to predict sequences well, these models somehow learn representations that capture structure, again, world models that can be reused across a variety of tasks. So particularly we want to ask the question, given a foundation model, how would we actually evaluate whether this has happened? Has it somehow made the leap from accurate predictions to a quote-unquote reliable world model? Now, while this question, is asked in a modern context, the promise underlying foundation models is actually something quite familiar. And so what I next want to do is I want to introduce an example that we're going to use throughout this paper and throughout the talk, and that is predicting planetary orbits. So this is a bit of an odd example for an econ conference, but fun for a CS audience. So what I learned in high school physics was that Johannes Kepler, quite famously in the 1500s, accurately predicted the motion of planets in the night sky using a very particular model based on the geometric properties of orbits that he postulated. And while he could perfectly solve this prediction task, his model did not actually explain why planets moved in orbits, elliptical orbits. Of course, Isaac Newton eventually came along, and not only did he write down a general model, Newtonian mechanics, that predicted orbits, his model could actually explain why the orbits had this geometric structure, using much more fundamental forces. So on this specific prediction task, orbital prediction, who was right? Well, technically they both were. They both wrote down models that yielded perfect orbital predictions, but of course Newton provided something far more general. In particular, he provided Newtonian mechanics, which gave us the tools needed to solve a variety of downstream problems by appealing to the same underlying logic. So, in a sense, in this specific example of planetary motion, Isaac Newton actually provided us with a foundation model. So, in the context of this example, the question we want to ask in this paper is, suppose we replace the physicist with a foundation model to do planetary orbit prediction. What would it mean for such a foundation model to somehow capture Newtonian mechanics in its underlying representation? Of course, we can ask the same question for any of these foundation models I've mentioned in economics as well. Suppose we replace the economist with a foundation model. What would it mean for such a foundation model to capture known structure that we analyze in economics? Perhaps known measures of human capital, market beta, etc. So what we tried to do in this paper is we tried to ask this question, how could we evaluate whether a foundation model has actually captured some reliable world model? And we wrote down a framework and a technique for thinking about how to answer these questions. The key idea in this paper is that the implicit world model of a foundation model is going to be revealed by how it extrapolates on small data sets. And in light of this idea, we propose a specific method that we call inductive bias probes to answer it. An inductive bias probe is going to operate in 3 steps. We're going to draw synthetic data sets under some true hypothesized world model. We'll then fine-tune a given foundation model on those data sets. And then we're going to compare how the foundation model extrapolates relative to the sorts of extrapolations that would be done under the world model. Then I'm going to go back to that motivating example and apply these inductive bias probes to several foundation models of orbital mechanics and ask, have they actually recovered Newtonian mechanics? So just at a very high level, what's the key idea? Well, when we use foundation models, by applying them or adapting them to various downstream tasks, at their core, they are just learning algorithms now. They take in some data sets and return prediction functions that go from some feature to an outcome. So as a result, a very classic result in statistical learning theory applies, and that is the no free lunch theorem. So what does the no free lunch theorem really state at an intuitive level? It states that because many functions can explain a finite data set equally well, learning algorithms must generalize based on some inductive bias. In other words, they must have some way of picking among functions that explain the data. So loosely speaking, inductive bias is a formal term in machine learning for a learning algorithm's baked-in preference to guide how it extrapolates from limited data. So in the context of our paper, the question we want to ask is, for a foundation model, what inductive bias is it picking up through the pre-training step? So to answer that question, we now have to introduce what we mean by a world model for these contexts. So we're going to be thinking about world models that place restrictions on the type of tasks or functions that we might encounter based on some implicit state space representation. So in other words, there might be ways of grouping together inputs into the same state that I'm going to organize in columns, and any task under the true world model has to respect that state space structure. So inputs that get mapped to the same state have to be given the same output. So as a result, the world model has its own inductive bias. You must extrapolate in ways that respect its underlying state space. So in light of these two ingredients, what we're going to specifically ask is, can we test whether a foundation model's inductive bias is toward a given world model? That is, does the foundation model, when it's fine-tuned, actually extrapolate in ways that respect the state space? So how are we going to operationalize that idea? In the paper, we write down this specific technique that, again, I mentioned. We call it inductive bias probe, where the idea is we're going to simulate a bunch of synthetic data sets consistent with the world model, fine-tune the foundation model on that data, and then examine how it extrapolates. By comparing the functions learned by the foundation model against the world model, we'll then evaluate whether it's recovered some structure. So going back to the earlier example, think of someone trying to extrapolate in a new context using the principles of Newtonian mechanics. To do that, they would calculate objects like the masses of the relevant objects, their relative positions, their relative velocities, and use that to make predictions about what would happen. So if a foundation model was using Newtonian mechanics, it should behave as if it does the same. It's the core idea. So looking at time, I'm going to just speed up a little bit. This idea of an inductive bias probe becomes very easy to think about in the context of a finite state space. And ultimately, we can write down specifically what the evaluation metrics are. But again, just looking at the time, I'm just going to jump ahead to the specific example here. So after writing down this framework, writing down formal evaluation metrics, we're going to try to revisit this earlier example of orbital mechanics. So what we do is we generate a synthetic data set of about 20 billion observations where we simulate basically galaxies with suns, planets orbiting around them. And then we're going to take that data and train our own foundation model about a transformer with about 109 million parameters to do next token prediction on these orbital trajectories. Now, when we do that, this transformer, like Kepler, makes extraordinarily good predictions. So if you evaluate the quality of both its next step predictions on orbital mechanics, it looks great. You can have it simulate orbits, and it also looks like it's doing a fantastic job. So this raises the question, if this foundation model can do orbital mechanics just as well as Kepler, has it somehow learned Newtonian mechanics? Well, each galaxy in our data set can be summarized by a sequence. It's governed by the masses of the suns, the relative velocities, the relative positions of each planet and the sun. So if the foundation model behaves as if it's calculating with Newtonian mechanics, it should extrapolate based on this state vector. So we can apply our inductive bias metrics to this transformer, and what we generally find is that its inductive bias is quite strongly not towards Newtonian mechanics. It often makes similar predictions for orbits with different states and vastly different predictions for orbits with similar states under Newtonian mechanics. Now, I didn't actually define any of the axes on these pictures, so this is a bit meaningless to you. But what does this mean in practice? So in practice, we're going to take this pre-trained transformer and ask, well, what would happen if we fine-tuned it on a data set to predict the force vectors between planets? Of course, I learned in high school physics that force is a very simple function based on the underlying state space here. So what would this foundation model actually do if it was fine-tuned to predict force? So what I'm plotting here in a nice GIF made by Peter is on Your left-hand side is, what would be the true force vector calculated from a planet orbiting the sun under Newtonian mechanics. The right-hand side is what is the predicted force vector you get if you fine-tune this transformer to actually solve this force prediction exercise. And I know enough physics to know that's not what force should be in this example. So then you can ask the question, well, if it's not uncovering, Newton's law, what force law does it appear to uncover? We're going to use symbolic regression techniques to try to estimate this. Well, first, as a sanity check, suppose we simulate data under Newtonian mechanics and we apply the symbolic regression technique. What do we get? We actually get the correct force law. If we instead generate trajectories under this transformer and we apply the same techniques, what do we get? We get something that is vastly more complex. It does not look like the true force law. But what's even more interesting is we can apply the same techniques on different subsets of our data, and the transformer actually appears to be learning heuristics applied to different galaxies. Now, as a last step, someone may say this is a model we pre-trained ourselves. Perhaps we didn't train this transform particularly well. So we also included an exercise where we ask how do large language models with reasoning perform on the same task. So we consider 3 advanced reasoning models from leading companies. We provide orbital trajectories and context and ask them to do the same force prediction exercise. And these all large language models with reasoning also struggle to systematically recover the force law. Now, that's sort of part 1 of the paper, which is asking, do these foundation models have an inductive bias towards the underlying state space or world model? If that's not true, what instead is their inductive bias towards? So the second half of the paper tries to investigate one particular hypothesis based on their pre-training objective, which these are all foundation models that are pre-trained to do next token prediction. So if they're not recovering the underlying world model, perhaps they're doing just enough to perform next token prediction well. And you can investigate this systematically, and what we generally find across an array of examples is that foundation models are only recovering enough to do well on their pre-training objective. In this context, that's next token prediction. So to wrap up in the last couple of minutes, these evaluation metrics that we write down suggest that current foundation models on their own appear to have poor inductive biases towards common world models in settings that computer scientists use as test beds. So this raises the question of, where should we go next? Well, new training procedures could attempt to directly optimize these world model metrics we write down. For example, there are different architectures that explicitly try to track a state representation. We could think of different pre-training objectives than next token prediction. In the paper, we have some preliminary results that suggest basically large-scale foundation models that explicitly try to track state do much better than transformers. The sort of heuristics that we point out appear to be associated with the properties of next token prediction. So perhaps alternative pre-training objectives, things more like mass token prediction, might do better. But more broadly, what we view this paper as doing is if we're interested in the question of whether foundation models recover some underlying structure, it's valuable to have precise evaluation metrics to answer that question. These metrics can then help us understand, what's working and what's not working. Then, as a last bit, what I want to flag is everything we've done in this paper, which we view as a preliminary step to answering this question, focuses on a setting where there is some known correct world model that we're training a foundation model on. Think about orbital mechanics and orbital trajectories and Newtonian mechanics. But what about all the sorts of settings we encounter in science where we have some known structure, but we reasonably believe that our structure is incomplete? It doesn't fully describe the data that we analyze. I would argue that basically all of the settings that I flagged in economics probably fall into that category. Well, here I think this question of whether foundation models recover some known underlying structure actually is an opportunity for us to do science. In particular, conflicts between foundation models and the sorts of structural models we write down in economics are really opportunities for discovery and insight. It suggests the model is picking up something in the data that's not captured by the structure we've written down. And I think that's a very exciting direction for economists to explore. So that's all I have for you. I think this is a 10-minute interruption.
7 minutes early. Okay.
Oh, I did?
So now you have 17 minutes for discussion.
Oh.
Go on.
Oh, I'm sorry.
Yeah, no, you're good.
I was going by the clock here. My bad.
Okay, the floor is open and we have microphones. We're going to use microphones. Go to Tosca.
Wait, I'm going to get the first question?
Well, she gave you the
what about
microphone.
Jerome?
That's power.
Okay, all right. So first, this is great. I love this paper. I've actually read it twice. I guess the question is, when Newton was doing this exercise, right, he knew that he was trying to develop a general principle, and he probably didn't just get it right the first time. He probably had some additional, I don't know what he had to evaluate whether he was getting it right, whether the only data set he had was these trajectories, or he had other information to think with. But the model isn't, you're not ever asking the model, are you, to provide a systemic characterization as opposed to simply a prediction? So, I feel, again, I think this is super informative, but it seems heroic to think that without knowing that was his objective, it just would have accomplished that due to some good fortune of inductive bias.
Yeah, absolutely. So, everything, so I would say a couple of things. So first, in for the figures I was showing you, I agree, you're almost asking for something very heroic. You're taking a model that's only pre-trained to do next token prediction on orbits and asking it to, somehow does it have baked into it some structure that works on these variety of other tasks. So one is, I think, that intuition is actually underlying a lot of, how these models get used in practice. Now, second, you could say, well, perhaps we shouldn't just be only pre-training these models to do next token prediction if we do a variety of different, post-training steps after the fact, or rather than just optimizing only on the narrow objective next token prediction, incorporate other objectives in training as well, that might improve things. I think these are all very reasonable hypotheses. And so that's why, to me, I think what's really, what I hope is a one takeaway of this paper is, this is a question that we can make precise. We can write down evaluation metrics. I encourage people to try different architectures. We tried different architectures. Try different objectives. We didn't try different objectives here, and actually see, do they move the needle on these evaluation metrics right now? Yeah.
Oh, fantastic stuff. Really fun. Two quick questions. Well, actually, one quick question, one perhaps less well-posed question. Quick question is there any relationship between what you're finding and overfitting in more general machine learning?
Yeah.
Now, the second question is a bit sort of more complicated because, I guess the virtue of your paper is to hypothesize that what the AI enthusiasts say about foundation models is right, and that under that hypothesis interrogate them. But an alternative is that the foundation models are just language models, and all they're doing is that they're mimicking human language with some human knowledge. If so, that's very different than understanding physical laws. Certainly it would require much greater modesty, but it doesn't immediately follow. I guess we were coming to this at the very end in the conclusion, but it doesn't really follow that we can learn much about the capability of the foundation models to be language models that we can communicate with. They can mimic interesting human and then sometimes give you some information because they find that in their pre-training data set. That might still work, maybe subject to some overfitting or not, but we're not going to be able to deduce that from the overfitting in the very difficult problem of orbital trajectory analysis.
Yeah, those are both great questions. So first on the connection to overfitting. So I think your intuition is in the right direction. And I think about this, and if I was reading the clock correctly on the laptop, I had a slide ready to go for you. But really, I actually think of what's happening here is more in line with, there's this sort of classic idea going back to, Leo Breiman makes this point in his old Two Cultures paper of what he calls a Rashomon effect in prediction. A Rashomon effect in prediction problems. So if you haven't seen, Rashomon is this old Kurosawa movie where basically there's a murder and there's 6 different witnesses and the detective goes to each witness and they describe the events very differently. And so what Breiman's pointing out is, when we write down these prediction objectives, there are actually many models that will do well on the prediction task, but they may have very different properties. And what's happening here, coming back to David's point, is, if we're just optimizing the narrow objective of doing next token prediction, there are many different ways of accomplishing that feature. Kepler versus Newton is a classic example. And so as a result, because there are many different models, when we're writing down architectures, they have their own inductive bias of picking between these alternatives. And the ones we were writing down are for various reasons, their inductive bias is not towards picking, say, a parsimonious representation of the domain that may be useful elsewhere. And then second, I think, for me, what I find interesting about this work is is twofold. One is, for a language model or foundation model to be useful, it doesn't necessarily have to obey sort of some world model that we've written down. And in some other work that Keyon and Sendhil and I have done, we've sort of tried to take that seriously and think about if people are making generalizations about model capabilities, how might they still be able to use this in practice? But I will say, going outside of language models, if we look across the sciences, I think the hope of using, say, foundation models on proteins in biology, on reaction predictions in chemistry, and on these economics examples, is that these models may be noticing structure that we as researchers haven't. And putting my sort of econometrics hat on, I think it's then useful to study these models in domains where we have a sense of what's going on and seeing, can they actually recover structure that we've written down? And so I would almost differentiate the use cases here. One, there's sort of these as tools out in the world to help us accomplish things, versus these as tools to try to uncover structure that we might explore scientifically. And that's why I wanted to end on this point of conflicts between foundation models and settings where we don't fully understand is not a problem. I think that's actually an opportunity.
But I guess just to follow up on that last
Use the
point.
mic, right? Because we have some online.
I mean, your last part of your answer is particularly very interesting, but then it relates back to overfitting. So it's impossible to expect that these models wouldn't then overfit, because they're going to condition on parts of the problem that are irrelevant given the sample. So it's sort of full circle back to some sort of overfitting.
Yeah, I mean, now I guess, so I think it's a great question. I think really now we have to dig in, when I read in this last bullet point, when we see a conflict between an ML model and, say, some known structure, what do we do with that? Do we take that as ground truth that the model is right? Or do we take that more as a hypothesis that's then worth exploring in further work? And I think it's sort of, other work that I've done, that Sendhil has done, I think, I won't put words in his mouth, but I'll put words in my mouth. I think that's really the direction to go, is these are opportunities for hypothesis generation that we should then explore.
In the language model case, don't we know from results in interpretability that the world models are quite rich? And for example, that they know that the Eiffel Tower is in Paris, and if you change that fact, if you say that it's in Rome, they'll adjust a bunch of different things in how they answer. And does that mean that there's something special about language models that are distinct from, say, physical laws, or you just think that's a specialized case?
No, I think it's a fantastic question. So, taking a step back, I'd say there are broadly two perspectives on how we might try to understand what models can and cannot do. And even within this literature on world models, sort of one line of work is what we're doing here, which you might call sort of a more functional approach. Take these models of black box, examine how they behave, the particular input-output structure, and ask what are the properties of it. The other route is what people would mostly call mechanistic interpretability. And the idea there would be, let's actually try to go inside the representation, particular, nodes in the network, and ask, do this behavior of those nodes sort of predict outputs? And I would say there are two issues that arise that I think are genuinely non-trivial. One is sort of one common technique we talk about in this paper is using what are called probes. Let's take the representation, try to predict features of the state. There it's not really clear what's the right, in technical weeds, what is the right sort of function class to be allowed to fit on top of the representation so you don't overfit. Another bit is, even in examples where we know there are particular nodes, say, that encode the Golden Gate Bridge, those same teams of authors, Chris Olah has a fantastic blog post about this, where he points out that there's really just a dark matter in the workings of a transformer. While we can ascribe meaning to maybe 1%, there's 99% that we don't understand. So this is not to say that I find that work amazingly fascinating, but that work does not imply that we fully characterize what's going on within these models. I think it's generally an interesting question. How do you sort of reconcile this mechanistic perspective and functional perspective? I disagree.
over here.
Thanks. Can you say more about the so it didn't get Newton, but it did get these sort of galaxy specific laws. Like, what are those? Are those just like less parsimonious versions of Newton, or are they interestingly different? Or
No, so they're let me flip back. They're all interestingly different, because if you take so basically what those laws are being fit are trying to explain what is the predicted force vector implied by the transformer. So it's not that those functions, if you just look at, again, the input-output structure, you run the same inputs, you get the exact same outputs as Newton, you actually get meaningfully different force predictions. And again, I think this comes back to sort of questions that David and Daron were raising. These are models trained to do next token prediction. There may be many models that do that task well. The inductive bias for say, the specific transformer architectures we focus on, is not towards a more parsimonious state representation. But one thing I didn't get a chance to talk about is if you instead think about architectures like Mamba, actually just try to just brute force fit LSTMs on the sorts of evaluation metrics we write down, they actually do perform meaningfully better. And those are all architectures that really explicitly try to track a state representation and do prediction.
Other questions? You have 4 minutes to show us another slide or whatever you want.
No, I'm happy to cede the time.
Okay. Well, thank you very much.